Hello everyone. In this video, we are going to use half circuit methods to solve out the problem of differential amplifiers. And we are going to use the method to derive the AD, the differential mode gain, and ACM, the common mode gains. And to begin with, we need to realize at this point here. This point, we assume the current source is ideal with infinity output resistance. This means there is not going to have any leakage current going down. And with this in mind, this current source can be assumed as open circuit. And the M point here, the middle point here, has a fixed voltage. The voltage there is forever fixed. And we can assume this point as the so-called virtual ground. And this ground is not very much different from the physical ground, with an exception that there is no current going into this ground here. So in other words, we can actually assume the circuits as two halves. First, we are going to take the output to here, from here, and the output from here, VO1, VO2. And because you can connect this point, you can treat this point as a virtual ground. And this ground is not very much different from the AC ground here. So eventually, right, we can just solve out the circuit, half of the circuit. We can just individually solve out half of the circuit. And then from there, we work out the voltage gain. And to begin with, let's say we have a definition where VID is equal to V1, V2, V1 minus V2, and this is the differential voltage gain. And VCM is equal to V1 plus V2 divided by 2. And with these two equations together, we can simultaneously solve for V1 and V2. And V1 will be equal to VCM plus VID divided by 2. And similarly, V2 will be equal to VCM minus VID divided by 2. And now we are going to solve the circuit and see if we can get the same result. We expect the result to be V out over VID, which is so-called the differential voltage gain. We expect the result to be one minus V2. And this is the result that we expected to get. If we cannot get this result, this means our method is problematic. So this is what we are going to expect. Now, so like what you said, right, we are going to try this method. and this one is ground, and this one is ground. And based on the information here, whether we use T model or pi model, uh, we can expect, but let's change this to small signal model first. So for the time being, let's, I've shown the transistor here is perfect. It has no early effect. So we can use T model to resolve it. The T model is IC1, 1 over Tm, and then, so this is the T model, and this is V1. For the time being, we ignore the early effect. And the output voltage here is going to be minus uh, uh, IC1 times RC. And IC1 is equals to, according to here, VI divided by GM. V1 divided by GM, and then RC. And do not forget, we have a minus sign here. RC1. Sorry, divided by 1 over GM, sorry. So we can get minus GMV1 C. And similarly, you can also get the VO2 as IC2RC, and we will have V2 we haven't finished here yet. We haven't finished here. Minus GM, and then V1 is equal to, assuming that this one is 0, is equal to VID RC divided by 2. And with this in mind, we can say VO2 is equals to minus GM, and then minus VID divided by 2. And the output is going to be VO1 minus VO2, like what we have here. And this is going to be this one minus this one. minus GM RC VID. And based on this equation, we automatically know the so-called voltage gain VID, which is also the differential gain. Which is equals to GMRC. So the result here is exactly the same as this one here. And you can actually just replace this with VD and VO as like this. So this is the so-called half circuit technique. And we can even use this technique to solve for uh, the common mode gain. So we use this technique, right? We managed to find out from here. And we are going to use the same technique to solve for the common mode gain. Now we have a, let's start from here, yeah. And we are going to have a similar circuit, RC and transistor V2, and this one is V1. And our topic is going to be common mode gain. First of all, for the common mode, yeah, well, we need to know what is the cause of common mode gain. Common mode voltage is V1 plus V2 divided by 2. And under the normal circumstances, there should not be any common mode voltage. One of the reasons why we have common mode voltage, we have common mode voltage gain here is because of the imbalance in the circuit. So I would say ACM is caused by imbalance in the differential pair. For instance, the emitter area of Q1 is not exactly the same as emitter current of Q2. No matter what, this imbalance causes IE1 and sorry. Because of this imbalance, we end up with IE1 being log equal to IE2 in terms of magnitude. IE2 is not equal to minus IE1. So if you look at um, this junction here, if IE1 is not the same as, is not equal to the opposite minus IE2, then what happens is that there will be the current going into the current source here. And we normally use current mirror technique to implement this current source. And because of the leakage current here, some of the current can go through here, and the pathway that enable this current to go through should be equal to the so-called early effect. And this early effects has a resistance R log here, and this R log is equal to R log is equal to VA divided by I. So in other words, you can assume the circuit is not ideal and we have a pathway going into the ground. We can assume we have this circuit. The equivalent circuit for the common mode gain as here. And also the input to the common mode to the differential amplifier. And remember, we have assumed V1 is equal to VCM plus VD, VID divided by 2. And V2 as VCM minus VID divided by 2. And now we are now dealing with common mode gain, and we are trying to use superimposition technique to solve for common mode gain. And in this case, VID is going to be 0. So we end up with this circuit. VCM. Now, you have RD here, and we are now trying to break this circuit into 2 halves. Now we break this one, right? This one will become a parallel of 2 R log. To R log. And eventually, we can just simply break this down. And this one will become a AC ground, AC ground. And we can use T model to resolve it. And we have IC, and we have 1/GM to RO. And the output will be captured from here, VO1. And similarly, we can do the same for the other branch of the circuit. And we don't really need this to be written down. The output is VO2. Now, VO1 is equal to, based on this circuit, VO1 is equal to V minus GM over 1 plus GM, and then the tail resistance to R0, and the resistance RC in parallel with the total resistance in here. You can just say RO out, and this one will be RO out, and this one will be equals to RO out, and for the time being, right? We don't need this part. Times 1 plus GM, and then 2 RO. So based on this simplified small signal diagram, we know that it is going to be 1 plus GM to RO. And we can simplify the circuit. We know that this value is much bigger than this one, and we end up with 1 divided by 2 R0 here. And we know why this value is much bigger than this one. So the approximately V out is equal to RC to R out, and times this is just the voltage gain. Sorry, V out over VCM, right? Is this much, and finally we get this one. And we have defined this V1 and V2 have these relations, and we also can define the voltage gain, the voltage output, which is equal to um, VO1 minus VO2 uh, as ACM times VCM, and then plus AD divided by 2, and then VID. Uh, and with this in mind, we can, based on this equation, we automatically know um, the uh, common mode gain ACM is actually equals to uh, this value. This one becomes 0, yeah, and that's why I said V out is this one, and we have shown V not as 0, VO2 is as 0, and that's why we end up with the common mode gain as RC divided by 2 R naught. Legally, you can use this formula to work this out. Now, what we have done is the simple cases. And what if we have more complicated structure, like for instance, we have tail resistance. VCC. And we have V1 and V2. And we are going to use the current source to supply bias current to both branch. And the output is to be tapped from here. And based on this, the detail of this circuit, we can immediately draw the half circuit. The half circuit is going to be um, and this one V1 we use VID, and then V out, and we know there is a early resistance here, and this will be the circuit for the differential voltage gain. the half circuit for differential voltage gain. For AD. And this one is the full circuit. And if we want to find the common mode gain, we can just simply use half circuit technique. And this one will be VCM, and this one will become O. And the tail will manifest as 2 R naught. So based on the information given here, we know the gain for this half circuit is G minus GM 1 plus 2 GM R naught RE should be. And then the total output resistance, which is RC in parallel with R naught 1 plus GM RE. So this is the differential voltage gain for this circuit. And for this one, it is very similar. The only difference is the tail resistance has additional 2R naught. So for ACM, it is based on the similar formula. One plus GM and RE plus 2R naught. And similarly, the output resistance, the total output resistance will become RC, and then R naught, and then 1 plus GM, and then RE plus 2R naught. So this is the common mode gain for this circuit. And I think for this video, I think we have already done enough. If you have any question, please leave your questions to the comments box, and I will try to answer your questions. Okay, thank you. Bye bye.